Hi, this is Charles DiMaggio, and welcome yet again to our For Epidemiologists. In this screencast, I want to talk about categorical data analysis. Epidemiologists spend a lot of time working with categorical data, in particular dichotomous data, where someone is sick or not sick, dies, doesn't die, ill, not ill, takes medicine, doesn't take medicine, is exposed to something, is not exposed to something. And R comes with any number of tools that make categorical data analysis actually quite simple and quite intuitive. So what I'm going to talk about is really just how you can get at the kind of categorical epidemiologic data that we work with, and some of the packages, two packages in particular, epicalc and epitools, that make these kind of analyses easy. So classically, epidemiologists work in a 2x2 world where the cells of the 2x2 table are, at least in my experience, arranged in this way. And this basically means that people are exposed or not exposed across the rows here, and they have disease or don't have disease across the columns. And we have any number of calculations we could make based on that. One of the most common is the odds ratio. And the odds ratio is basically, there's two. There's the disease odds ratio, which is the odds of disease over odds of not having disease. And in this group here, and you get the cross product, you end with AD over BC, which is a classic calculation. Kind of get the same thing for an exposure odds ratio, to tell you the truth. And we do take advantage of that. It is somewhat invariant. It's a very robust measure. But if you were interested in doing some kind of calculation with a 2x2 table in categorical data, I think it would be relatively straightforward to do that in R. And if we had, for example, I have some code up here, our digitalis data, which we've worked with before, we'll read it in to the R session we're working with here. And we have a digitalis data set now. I'm just going to get rid of this right here so it doesn't distract too much. We have the digitalis data set that I'm calling dig right now. And we recall that the digitalis data set, there's a bunch of names here, was a study of the effect of digitalis on myocardial infarction mortality. And there is a variable called treatment, a variable called death. We could do a quick table, a quick 2x2 table of these two dichotomous variables, and we end up with this 2x2 table, and this corresponds to the A cell, B, C, and D. We can actually extract these elements and do a quick calculation of this, and here we just do that right here. And we have this table now, and if we want to see what my table looks like, just write that right here. And here is our table. It's the exact same thing as this table. We just saved it to an object. If we want to extract the various elements from this table, it's simply a matter of indexing it. So this is row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2, which corresponds, as I said, to A, B, C, and D. And we can extract each one of these elements and put it into the formula of A times D over B times C. And if we do that, we get our odds ratio, which is 0.98, which we've seen before, which basically indicates that there really is not very much effect whatsoever. Now, if we wanted a confidence interval on this, we could take the advantage of the very nice property of odds ratios. And working on the log scale, we know that the standard error is the square root of 1 over A plus 1 over B plus 1 over C plus 1 over D. Makes it a little bit straightforward to calculate something. And what we can do then is get rid of this once again. I've created that little calculation over here. So I have 1 over, and the A cell is my 1, 1 cell, plus 1 over the B cell, plus 1 over C, plus 1 over the D cell. And we're taking the square root of the whole thing, and we're saving it as an object called my standard error. And we do that right here. And we see that it's 0.05. Remember, this is on the log scale. So when we do a quick calculation of the upper confidence interval, we take the log of our odds ratio and add 1.96, which is the classic standard deviate for that, times our standard error, save it to the upper confidence interval here, and then when we exponentiate that, we get the upper confidence interval, upper 95% confidence interval for that odds ratio. Do the same thing for the lower. Only difference is we're subtracting here. Get that. And we see the lower, it goes from 0.89 to 1.08 on a point estimate of 0.98, really not very much effect of treatment whatsoever. Now, of course, you will not have to do that because there are very nice people, including Tomas Aragon, who we've spoken about already, who have done this for you and created a package. It's a very nice package called epitools. And I'm not going to go through the installation process. I already have it installed, but if you don't have it on your machine, use install packages, epitools, in quotation marks. I'm just going to bring it into my session using the library command. Now, epitools is loaded, and there is a very nice function in epitools called epitab, and you could look at it, and here is the help page for epitab. I'm going to make this a little bit bigger. The most important thing about this, I think, first of all, you should always look at the help page if you're not using it before. What I usually do is I just go down here and start running through the example. That's the way I tend to learn, but folks have different approaches to that. What is very important here is that, and Dr. Aragon says, notice the expected structure of the data to be given to epitab. Very important. And it's a little bit different than you might expect. It certainly is different than what I learned. What he has is he basically has his data set up where the reference cell, no disease, no exposure, is in the A cell. That's not really the way I learned it. As I mentioned here, if you look back here, basically I've always sort of learned it as exposure, and that's the A cell. What Dr. Aragon has is something really quite different. If you have exposure and disease, it's minus, plus, minus, plus. Whether that's the way he learned it, or whether it has to do with really the default way that R returns a table. And I think it has as much to do with that as anything else. Because if you notice, when we did our quick little table here, we have it's set up like this. Now, I didn't worry about it, right? I just calculated my odds ratio as if this was set up the way I wanted it set up, and I can get away with that because of the relative invariance of the odds ratio calculation, that cross product. But that will not always be the case, and we will see that in a moment. In any event, if you want to use epitab, it's really quite straightforward. Epitab will take data in three formats. It will either take a table, or it will take the factors. So, for example, it will take the variables themselves, or it will take the row-wise cell values for that table. So you have three ways of doing it. And here, let's just run through it relatively quickly. So we have epitab, we have epitools loaded, and we know what epitab does. Let's create a little table called table 1. And here is our table. It's the exact same table that we had when we calculated, when we extracted the elements of that matrix before. And if we just submit that table, table 1 that we just created, to epitab, we get a very nice odds ratio calculation. Here is our point estimate, 0.98. Here is our upper and lower confidence intervals. And kind of nice to know that our little calculations were pretty much on the money. As I said, you could do it a couple of different ways. In this way, I'm just doing a different calculation. I'm using epitab again, but instead of giving it a table, I'm giving it the two factors that go into making up a table, and I'll get the same answer. Or I could give it the four cells, row-wise, which are 2209, 1194, 2209, 1194, 2116, 2216, and 1191. I just give those as an argument to epitab. You get the same answer right here. You can see it, right? So there's the lower, the upper. Here's our confidence interval over here. One thing you could do is, like I said, there is this question of giving the data to epitab in the right format. If I were to reverse the rows, there's a little option in epitab where you could reverse things. So here I'm reversing the rows. I get the wrong answer because all I'm doing is reversing those rows. Now, if I reverse both, which is what I did, which is the way we sort of like think of it, I do get the right answer. Just to tell you that this option is available and that you can use it, but be careful, make sure that the data is in the format that epitab wants. One other little example we could do here is, let's say, for example, I wanted to do a stratified table, and I want the odds ratio for the association between treatment and mortality for the age group less than 50, the age group between 50 and 65, and the age group greater than 65. all that takes is a little indexing. So now I'm creating my table. I'm calling it table 1 using the table function. And here I am indexing treatment to just where age is less than 50. And I'm indexing the death vector from that data set to just where age is less than 50. And here I'm doing it for age less than 50 and greater than 50 and less than 65. Do the same thing for death. And here I'm doing it again for a third table where age is greater than or equal to 65. I'm creating 3 tables, and here we can see them as I'm creating them. And now I'm going to run epitab on each of those 3 tables and save those results. So for table 1, I'm going to save the result as OR odds ratio 1. For table 2, I'm going to save it as odds ratio 2. Run through that relatively quickly. So I have these 3 odds ratios now, right? Saved as objects. I want to extract out the odds ratio and the lower and upper confidence intervals for each one. And how I would go about doing that is, first I would look at the structure of this object, this epitab object. And it is a named, here's my structure example. It's a named list of 4 elements. The element I am interested in, the first one, is called or named tab. And if I were to look at that, here it is, OR, it's named, OR1, $ tabs, because it's named, I can use that. And here is that tab. And what I really want is basically the second row and the 1, 2, 3, 4, 5th, 6th, and 7th elements of the second row. And it just takes a little indexing. So now what I'm doing is I'm naming the object, naming the element of the named list within that object that I want, and then indexing from that named element the elements that I want. Second row, 5th and 7th columns, 5th to 7th columns, and here I'm getting what I want. And now I'm just going to save that to one called young, relatively young, less than 50, middle, old, and I'm just going to bind those together using a data frame command. And now here is my little table of the 3 odds ratio for each age group. There are any other number of categorical data analysis tools within R, and you can familiarize yourself with them. So just using this table 1 that I created over here, you can request a Fisher's exact test using the Fisher.test function. And here is our Fisher's exact test, and we see that the odds ratio for whatever association we found is not statistically significant. We could do if we were to want to, we could do a chi-square test on those same data. See, the chi-square test is even less significant. If you would like to calculate your odds ratio within the setting of a logistic regression, it's relatively straightforward. We already went through this. So we use generalized linear model. We write our model statement, death, as a function of treatment. And here we're going to control for gender and see if this makes any difference. We'll specify the data set, specify the binomial and logistic family, the log link, and we'd run that. And if we ask for our summary, we get the summary on the log scale. And we could exponentiate that to get the summary on, here's the coefficients. And we see that once again, treatment really has little or no effect. And there are any other number of ways you can manipulate this. So for example, here I'm creating an object called a summary of coefficients, which is a summary of my model coefficient, which is basically this. And I am going to save that as an object. Then I am going to extract the estimate from it, the estimate for treatment from that, which I'm calling estimate. Then I'm going to use my exponentiation of the sum coefficients for each one. I'm just calculating another upper and lower confidence interval over here, just doing it myself. And actually, there are ways you could do this. I'm just going through the process of saying if you didn't know how to do it, you could actually do that. I'm going to bind those together. And here, for example, is how I might actually go through the step-by-step process. If I want to save a little time, as I said, I don't have to actually do this. There is the coefficient function that will, and the confidence interval function that will extract all those things for me, and I can just do that and see bonded together and get basically the same thing right here in a very nice fashion here. In any event, that's a quick introduction to categorical data analysis in R for epidemiologists.